Yeah, so welcome in everyone. My name is Thomas, and today I'll be presenting about the effect of atmospheric conditions on point spread function, or abbreviated as PSF. Today's date is 21st September 2024. So again, welcome. My name is Thomas, and I worked in the Polygence mentorship program under mentor Kristen. My hobbies include astrophotography, reading J.R.R. Tolkien literature, and watching soccer. I'm a Tottenham Hotspur fan. So to give you guys just a brief agenda overview, first I'll be going over the background and the motivation for my research project, which will lead me into my research question. Then I'll dive into a little literature review to justify my background and research question. Then I'll review the methodology that I used to conduct my original research study, and then analyze and discuss the results. Then I'll conclude my presentation. So for some initial background of my research project. So what is PSF? What is point spread function? And what does atmospheric conditions have to do with it? And how does this have to relate with astronomy? Well, the main focus of my research presentation here today is astrophotography. Like I mentioned before, I'm an amateur astrophotographer who works to photograph deep sky objects outside of our solar system. So on screen, you see two images, the first one being of the Andromeda Galaxy, and the second is the Rosette Nebula. Now, it is my hobby to photograph these objects, and I've photographed a variety of objects over my astrophotography career. And while astrophotography has widely been limited to like space agencies and NASA and professional astronomers, over the past few decades, off-the-shelf amateur astronomy has become much more popular and accessible, which has allowed me to photograph these objects just from my backyard. So what does astrophotography have to do with the atmosphere? Well, unless you have access to really advanced space telescopes such as Hubble and the James Webb Space Telescope, all amateur astronomers and professional astronomers have to work against the same issue of atmosphere because they're photographing these objects from the ground. Earth's thick atmosphere disturbs the light from stars and other objects, and in short, the light from the stars is bent, reflected, and distorted, thereby impacting the authenticity of the image that you're taking, and then the stars are disturbed and distorted. So to exemplify this further, while it might not be readily apparent when you're on the ground, lying down on a clear, sunny sky, when you're on an airplane, like this photograph taken by me on an airplane, you can see that even on clear days, you can see that the sky is very hazy and the transparency isn't very good. So this is what astronomers have to deal with. This is another photo. You can barely see the ground and it's very hazy, even though there's no clouds in sight. So what does this all have to do with point spread function? What even is point spread function? Well, it is a quantifiable value that quantifies how much the light is distorted. So it basically gives a numerical value of how much the light from the star is spread out by the atmosphere. So you can see here on one of the photos I took, this is a small star in the background, and the pixels that it takes up in the image is the point spread function. So it's how much it's spread out. And the atmosphere makes the point spread function larger because it spreads out the light more. So a very large point spread function indicates that the atmospheric conditions were really bad on a particular night. And if it's smaller, then the atmospheric conditions were better. Now, figuring out the point spread function helps astronomers in image processing and understanding just how much the atmosphere played a role in their photo. Now, this leads me to my research question. How does specific atmospheric conditions affect the point spread function of stars differently? So basically, how do specific conditions have any trends or patterns or the specific effects of the point spread function? So are there any visible trends or patterns that I can see that has not been established by previous research? So to go further into point spread function, this is an image I took of the Pleiades star cluster Messier 45. And as you can see, when you zoom into the photo, these stars here that originally look like very small points are actually spread out over the image. So this is the point spread function. So yeah, just a literature review to justify my background and my research question. These two sources that you see on the left did a really good job of explaining point spread function and its role in astronomical data analysis. On the atmosphere, the Las Cumbres Observatory does a very good job defining that the point spread function is caused by atmospheric distortion, which blurs and disturbs the point of light that enters the atmosphere. Another source goes into more in depth of how the atmosphere actually interacts and says that many factors such as haze, aerosols, transparency, pollution, and humidity all impact the atmospheric visibility. All these factors are in play when you're considering how well the atmosphere is on a given night. So how will I answer my research question? Well, my methodology involves me using my own astronomical imaging rig, which consists of the Fujifilm X-A7 mirrorless camera on top of a equatorial mount, which stabilizes my imaging system relative to the Earth's rotation. Then I had a refractor telescope to magnify my field of view. My data collection procedure involved acquiring 30-second exposure photographs of 4 different target stars under very different atmospheric conditions, which were recorded in visibility in miles using a weather database at fixed settings of 400 ISO. Then I used the software PixInsight Dynamic PSF tool to automatically generate point spread function fits so I could analyze the full width half maximum of each star, which is basically just the radius of the star in the X and Y axes, which can be generated using point spread function. And then I used Python to visualize the data by plotting them in graphs. So my targets for this research project was the star Arcturus, you can see here on screen, the binary star system Albireo, and the bright star Vega in Cygnus. I also had a fourth target in the background near Vega called TYC 3105, I believe, and it was a very small background star that isn't really visible in this image here. And here is just me analyzing one of the photographs I took of Vega. And on the right, you can see the little box of the dynamic point spread function tool. To clarify, PixInsight is an image processing software used by amateur astronomers to post-process their astronomy images. And dynamic PSF is just many of the tools that PixInsight provides. Now you can see, if you look closely, it presents the full width half maximum of the x-axis and the full width half maximum of the y-axis in pixels, and I combine these two values by adding them together and square rooting them. So here are my results at a glance. So just to start analyzing this data, the graph shows the full width half maximum as the y-axis and the visibility in miles as the x-axis. So Vega and Arcturus both have a decrease in the full width half maximum as the visibility conditions continue to improve, which confirms the other research studies that I analyzed that said that the visibility improving will improve the and lower the full width half maximum or the PSF. However, an interesting trend that I was notified about was this little diminishing return, this little flattening off of the curve at around 22 miles for both Arcturus and Vega. So as the atmosphere continues to improve, the point spread function starts improving less. It starts decreasing less. So this is a very interesting trend that I found. And for Albireo, there actually wasn't much of a flattening off here. And this might be due to the fact that it's a binary star system. It is mostly a linear graph, as you can see. Now, for the final smaller star, you see a pattern that resembles that of Vega and Arcturus. However, the data points that you see here are a lot more erratic and volatile compared to Vega, Arcturus, and Albireo, which I'll get to in my data analysis section. Yeah, so what do these results all mean? So um, these results for Vega and Arcturus allowed me to hypothesize that um, the diminishing return you see at around 20 and 22 miles may be due to the fact that as the atmosphere continues to improve and the factors that impact atmosphere, such as humidity, aerosols, transparency, and other factors such as wildfire smoke, you can take that all out of the atmosphere. You can continue to improve those conditions and have pristine atmospheric conditions. However, if you remove all of that, you still have the atmosphere that you're imaging through. You still have just the basic gases above our heads. You can't really strip that away from the Earth. Because this atmosphere still exists, just the point spread function just stops improving because you can't improve the atmosphere any further. You can't just take the gas above our heads out of the Earth. So this means that the diminishing return will eventually completely flatten out, as there's nothing you can do to really improve the atmosphere anymore, even though visibility might continue to improve. Yeah, so that was for Vega and Arcturus. For Albireo, the very linear trend was fascinating to see, and this might indicate that binary star systems are just impacted a lot differently by atmospheric effects, or just point spread function is interacts with the atmosphere differently. And a future research study, it'll be really interesting to see a future research study go in depth into binary star systems and just binary star systems, so not these other star targets, which are all singular star systems. Now, the last target definitely followed the trend of Vega and Arcturus, However, the volatile and erratic data points might indicate that because it's such a dim, small star in the background, the very small vibrations of the imaging system that I used might spread out the star a little more on some nights because let's say the shutter opening and closing might have impacted the data collection process. So while the still same trend was observed, this very volatile data indicates that sometimes astronomy equipment is not well suited to photograph these very small objects. So a more stable imaging system can be used to analyze even smaller targets in the future. So yeah, this leads me to my conclusion that this study confirmed the strong negative correlation between atmospheric visibility and the size of a star's spread already established by professional researchers in the past, and that my research study found very specific special trends, especially in the diminishing return area in the 20 to 22 miles of atmospheric visibility, and that binary star systems are impacted very differently, and the point spread function of binary star systems may be a lot more different than singular star systems. And yes, and small dim stars like TYC 3105 can feature erratic data points caused by a target's accessibility to small motions during the image capturing procedure. So yeah, that was my research presentation. Thank you for listening. And I have worked on a research paper about this and am publishing it into the International Journal of High School Research, if I may. Yep. Thank you so much, and thank you for attending.
Thank you so much, Thomas. What a cool and personally impactful topic. I'm actually really curious, how did you get into astrophotography? That's not something that I hear a lot of high schoolers
Yeah.
get into.
S- so I've been interested in space and astronomy for a really, really long time, especially when I was younger, and I read and watched a lot of books and videos about it. And one day I was just really like fascinated about photographing deep sky objects because these objects are actually not as small as people think. You don't need really big telescopes to see them. You only need around 200 to 400 millimeters of focal length to image these objects. They're actually pretty big in the sky. They're just really dim. So one day I just got out and pointed my camera out into the sky and see what I could find, and it just like snowballed from there. And over the months, I just upgraded my equipment and learned more procedures about it. And now it's really a full-fledged hobby of mine and a passion that I pursue as a high schooler.
That's amazing. And do you think you want to major in something related to astrophysics or astroscience?
Yeah, definitely. I want to major in astrophysics.
Very cool. Very cool. You and actually multiple people today who did presentations. So
Yes.
very
Yeah.
cool. Thank you so much
Mhm.
for the presentation. We had actually one question come in from Sanvi.
Okay.
How do you take the photos? Can you walk us through the actual process? Because we saw the telescope. It doesn't look like an
Yeah.
iPhone. So how do you how do you do it?
Yeah, sure. So the astrophotography process is actually just a lot more complicated than just pointing your telescope into the sky and obviously taking a photo because these objects are so dim. And there's a lot of light pollution that goes along with the image taking. So what I do is use my equatorial mount to automatically slew, so move the equatorial mount to the target I'm photographing by putting like the coordinates in a hand controller. Then as the target is centered, I start my image taking process, which is I use an intervalometer to set 2 minute exposures of the target. So the camera takes a photo for 2 minutes to let in as much light as possible. And the equatorial mount stabilizes the mount. So as the sky rotates relative to the Earth's rotation, the stars are singular points instead of being trailed across the image after as 2 minutes pass by. So I take a lot of these 2 minute exposures. I take around 100 to 200 a night, and I just leave it outside and I just go to bed. And when I get up, I take the telescope inside, see the 200-ish photos of 2 minute exposures it took, and then stack them together. So the stacking process is really important in astrophotography. It allows me to reduce the noise of the image, but increase the signal of the image. So the nebula I'm taking a photo of gets amplified, and then the noise is decreased as the images are stacked together. And the final product is around 2 to 5 hours of total imaging time. So then I process it using PixInsight and get the final result.
That is
Yeah.
incredible and so much work to get one image. So the
Yes,
image that you showed
definitely.
us is like many hours of
Yes.
photography and also post processing.
Yes, the images that I showed you is taken over multiple nights because
Um,
on one night I don't have enough time to get enough data to
uh-huh.
have a really nice image. So the Andromeda Galaxy I actually took over like three-ish, 5 nights in September of last year. Yeah,
Wow. That's really cool.
thank
Maybe
you.
that's something I'll get into too.
Yeah, it's a very fun hobby. You should definitely look into it.
Thanks so much, Thomas.